All right, hey guys, it's the Day Daddy here, and I just want to start as always by saying thank you for taking interest in my channel, and hope the content provided is useful for you. If it is, I'd really appreciate it if you guys hit that like and subscribe button so I can continue to grow and provide more quality content. I've got that out of the way. Let's get down to business. Today we'll be talking about the Bluetooth protocol, um, and more specifically, the Bluetooth protocol, the way it's evolved, the stack, the process of actually connection, the process of data transmission. We kind of be covering all of those things. And the thesis of this really is the fact that um, I'm doing some work in the lab right now, and we have a fair amount of Bluetooth devices that we're testing and using. And I realized that I knew next to nothing about the protocol itself, and it was readily implemented all over the lab that I work. So I decided I would kind of dig in and take a closer look at what's going on kind of behind the scenes and how everything works, and I would share it with you guys. In addition, there's over 9 billion Bluetooth devices so far and counting. It seems like it's becoming more and more prevalent every day, so it's something that I feel like everybody should have a little bit of an understanding of, and know something about. So let's get into it. Okay, so we'll start with kind of just a brief history of Bluetooth in general. So it was created about 20 years ago, or over 20 years ago now, to allow wireless communication between devices over short distances. Which, back in the inception of this, they really wanted to find a way to get rid of wired cabling, and this was kind of the thesis of why Bluetooth was invented. And you may be thinking, why is it called Bluetooth? And I was thinking the same thing. And apparently, it's named for a renowned Viking and king, King Harald Bluetooth, who united Denmark and Norway in the 10th century. And then similarly, the aim of Bluetooth was to unite PC and cellular industries with short-range wireless link. And apparently, this King Harold guy had a Bluetooth, and the runes for his name were this character and this character, H and B, and that's kind of how we got the initial Bluetooth symbol. So I thought that was kind of neat, a neat find. So fast forward to 1998, the Bluetooth Special Interest Group, abbreviated SIG, was formed, and to this day it's the kind of the governing body that standardizes, publishes, and revises the Bluetooth protocol. Initially, SIG was comprised of Ericsson, IBM, Intel, Nokia, and Toshiba, but today it has over 4,000 members, and counting. So that's pretty interesting. Okay, so I think one of the things that was confusing to me, especially about Bluetooth, is um, there's so much different information about the different protocol versions, and I think it's really helpful to kind of step through from Bluetooth 1.0 all the way to 5 where we're at today and kind of see the progression. I think it's really helpful, or at least was for me, to figure out what goes with what and kind of to make sense of everything. So that's what we'll do now. So starting with Bluetooth 1 to 1.2, in 1999, so 1 year after SIG was founded. Like I said, it was originally designed to replace the cabling of the time, or the cabling for the computer periphery. So, for example, the keyboard, mouse, all the things that you would plug into the keyboard. And it was specifically designed to replace this RS-232 serial port. I'd never really heard of this, but apparently that was, back in the day, that was what was used to link everything into your computer. So the idea was they wanted to replace that with something wireless. And the data transfer speeds back then, when version 1 was 732 approx kilobytes per second, and then 1.2 we upgraded to 1 megabit per second. Connection range was about 10 meters or 33 feet. Couldn't really transmit high audio quality at the time, had some significant security issues, and very high power consumption. So now we'll fast forward to 2005, and we have Bluetooth 2.0 or 2.1. Kind of started becoming standard in a lot of consumer products. Since kind of I remember when I started seeing Bluetooth, and we had a new data transfer. So it's called Enhanced Data Rate, or EDR. And if you're interested, you can go into more detail. I don't have time to go through it here, but basically, the long story short, it increased data transfer rates up to 2.1 approx megabits per second. The connection range was increased to about 30 meters or 100 feet. We lowered the power consumption. We improved the security with something called secure simple pairing. But the sound quality was still mediocre at this point. All right, now fast forward to 2009, we have Bluetooth 3.0 Plus. An interesting thing here, this actually allowed for transfer over Wi-Fi, which thought was interesting. I didn't know that. So most common Bluetooth versions for headphones, speakers, and portable media, and this actually is still the case today. Anything that requires a lot of rich media transfer still typically uses some form of Bluetooth 3.0. It also has super high transfer speeds of 24 megabits per second. The L2 cap layer, which we'll learn about later, had enhanced modes, and then also alternative modular receivers were introduced. So kind of at the physical layer, or the very most basic hardware layer that actually allowed for transferring larger files. Um, Enhanced power control, let wireless devices kind of adjust their power consumption as needed, which is a nice feature. It also introduced unicast connectionless data, which facilitated quick transfer of smaller amounts of data. The downside here was we had even higher power consumption because we were involved in Wi-Fi. Finally, 2010 we had Bluetooth 4.0, and this is the one of the most important slides here, because this is kind of where we had almost an entirely new protocol. Actually, not almost; it was an entirely new protocol that was introduced. But this was BLE. So nowadays, when you hear Bluetooth, more often than not, you're actually talking about Bluetooth Low Energy or Bluetooth Smart. Those are synonymous. But this was really designed more for IoT devices, specifically devices that didn't need as much like rich media transfer. They only were active, some of the time. Like for example, IoT devices like today we have smart smoke detectors and things of that nature, which they don't really need to be active all the time. So having these heavy connection oriented or heavier connection oriented protocol like the Bluetooth Classic wasn't really necessary. So they kind of made a whole nother protocol, which was a lot more lighter weight and consumed a lot less power, and they named it BLE and Bluetooth Smart. So in addition, they came out with Bluetooth Smart Ready, which was basically, think of the Bluetooth Smart Ready kind of like a hub. Or basically like your laptops, your mobile phones, things of that nature would have this Bluetooth Smart Ready, which would have would be able to talk to Bluetooth 3.0 devices as well as this new BLE. So it was able to kind of go both ways. So Bluetooth BLE devices and then Bluetooth Classic devices are not able to directly communicate with each other, but they can communicate with these Smart Ready devices. So this is like your laptop, think of it as a hub, and then it can kind of connect to all of the devices that may be using the Classic protocol or the BLE protocol, either one. So I thought that was neat. And again, the connection range increased. We're at about 200 feet at this point. There's due to some protocol level advances, there's less interference, so less interference from other protocols that use the same band, such as Zigbee and Wi-Fi and other things like that, which we'll talk about a bit later. There was improved hearing, improved data transmission with adaptive frequency hopping, which we'll touch on just a little bit, and then BLE data transfer. We're back at 1 megabit per second, but we are using less power. And so it was a trade-off here. We're not moving data at the same speeds, but we don't really need to because the devices we're trying to actually power require less data transfer. And really what we're getting after here is we really care about, at least with BLEs, we care about that low energy. We want to be able to have devices with really small power constraints to still have a wireless connectivity protocol that can support them. And then in this case, the audio quality significantly improved here. All right, now fast forward to present day, and we have Bluetooth 5.0, and it came out in 16. It focused on building off of the BLE improvements and providing a even better framework for IoT devices. So we increased the data transfer rate to now 50 megabits per second, increased connection ranges about 790 feet, which is crazy. New LC3 transfer. So basically the same audio quality, but now lower bit rates, which is super nice. Less power consumption still, increased message capacity. We're also backward compatible with Bluetooth 4. Dual audio features that you can connect to 2 different devices at the same time. That was actually really nice. I remember when that feature actually came out. And let's see, addition of slot availability. So again, we're reducing the interference with now cellular at this point. And then they introduced 5 new security features with this, making Bluetooth more secure. So there were some security issues with PLE, which I'll actually touch on in another video. Okay, so now I touched on it a little bit earlier, but I just want to really drive home the distinction here between Bluetooth Classic and BLE. So Bluetooth Classic refers to the versions of 1.0 to 3.0, and that's for devices that need continuous short-range data and audio streams. This is rich content, things like printers, in-car entertainment systems, like high quality headphones like your Bose and like Sony Mark IIIs and things of that nature. So really kind of more robust devices would be using something like this in a lot of cases. And in contrast, you have Bluetooth BLE or Bluetooth Smart, and this is version 4.0 and above, and this is really designed for you know, less advanced, or I'm going to say less advanced, but less consumptive devices, like maybe a key fob or a thermometer or remote or things that are not as resource intensive. And due to low power usage, like I said, it's ideal for IoT, and it has kind of list out some things that it's good for. I thought it would be interesting to kind of compare sorry guys, to compare some of the specs. So they both operate in the same frequency band, so that 2.4 gigahertz ISM band. But the original Bluetooth has 79 channels, and Bluetooth LE has 40 channels, but 3 of those are advertising channels. And one interesting thing that I wasn't able to find out through my research is BLE has this idea of advertising channels, which it uses to kind of form connections. And I couldn't find out whether or not there were specific channels on Bluetooth Classic for advertising. So if any of you guys know the answer to that, let me know. But the bandwidth for the original, the Classic, is 1 megahertz, and it actually increases to 2 megahertz with BLE. There is 600 hop second frequency. So basically what that means is we're going to switch channels 160 times every second, I believe. So, and that'll make sense in a second, but that's a way of making sure that interference is low and making the protocol more robust. These are different modulation schemes, or modulation techniques, I should say. This is the least complicated of them, and it's the easiest to implement, so it's kind of why it's used with BLE. These are a little bit more complex and require a little bit more, I think, a little bit more advanced hardware, so that's why they're used with Classic. But these can achieve significantly higher data transfer rates. One thing that's also worth mentioning is there's different power classes for different Bluetooth devices. So, I mean, I'm not going to go too much into it, but there's a class 1, which is the most consumptive, and then class 2, which is significantly less, and then class 3, which is significantly less. So just keep that in mind. Let's see what else. So we have in the traditional Bluetooth Classic, we have inquirying or paging, which is similar to advertising, but not quite the same. The difference is a little bit unclear, but I'll do my best to explain as best as I know. Yeah, I think those are the real highlights of the differences between the two. I think it's interesting to kind of see a side-by-side comparison. Okay, so let's look at the physical communication, how Bluetooth actually transmits its data. So, as we said before, it sends and receives data via the 2.4 gigahertz band, more precisely from 2.4 to 2.4835 gigahertz. And this is because, or the reason this kind of came about, is it may seem random to pick this particular band, but basically the ISM, the Industrial Scientific Medical, I guess it's the council, or the organization that is responsible for a particular bandwidth range, designated this as an unlicensed frequency. So you don't have to pay or have a license to use this. So that's why protocols like Wi-Fi and Zigbee and Bluetooth and others use this, because there's no licensing. So I thought that was interesting. I was kind of curious why they chose this, but that kind of makes sense why. And it's geared for, like we said before, short range, low power, low cost wireless transmission. Okay. So now getting a little more specific, the protocol transmits by doing something called frequency hopping spread spectrum. And what that is, and we're looking at Bluetooth Classic here, by the way. It's just an easier way to think about it, I think. But basically, the device, or each device, changes channels 1,600 times in a second in random order for robustness. Because if you look at this 2.4 to 2.485 band, there's 3 major protocols that operate in this band. So there's Wi-Fi, there's Bluetooth, there's Zigbee, there's actually others. So there's a lot of traffic that's happening on this band. So the idea is to allow traffic on this kind of crowded band without significant interference. We're gonna break this band up into small channels, small 1 megahertz wide channels, and then we're going to, in random order, at 1,600 times a second, we're going to change those channels. So in that way, it's very unlikely, or even if there is some interference, it's not happening all the time, or it's happening very infrequently. So in that way, we kind of minimize the effects of interference. You may be thinking, well, if we randomly change channels, 1,600 times a second, well, how will two devices communicate with each other? Well, before they actually start transmitting data, they agree upon a particular transfer sequence. Um, and in doing so, they basically mirror each other. So each device will have the exact same transfer sequence, throughout their connection with each other. Um, and that's kind of the main idea behind Bluetooth transmission and how it kind of interacts in a crowded bandwidth. There's also another idea of adaptive frequency hopping, in which case, so imagine we have all these channels, right? So each channel, based on its level of interference, is actually labeled as good or bad. And rather than using all of the channels as available like sequence paths, only the quote unquote good channels are used and selected. And after a period of time, the channel will be reviewed again, and then it will be reassessed as good or bad. So in that way, you can actually have different channels that are available. And in this way, with adaptive frequency hopping, all of the bad channels, or all of the really high interference channels, are cut out, and we're only using the quote unquote good ones. So I thought that was an interesting way to kind of do even better than frequency hop, or the base level of frequency hopping. Okay, so now we kind of understand how that the data is transferred via the air. Let's look at how the Bluetooth devices actually work and connect to each other on a device-to-device protocol level. So with Bluetooth, we have the idea of masters, slaves, and piconets. So networks are commonly called piconets, and a piconet is a master node, or a master device, you could say, which has up to 7 slave devices. So one master, and all of these are connected devices to this particular master. So, like I said, slave or master can have up to 7 slave devices, and one slave can only be connected to one master, unless it's a bridge device. So this brings us to the idea of what are called scatternets. So since you can only have one master and 7 slaves, well, how do you build a bigger network? Well, you allow these individual piconets to connect together. So one slave inside of a piconet can actually act as a bridge between itself and another piconet, and it is allowed, since it's a bridge node or a bridge slave, it is allowed to have connections to 2 masters in order to facilitate the kind of joining of the 2 smaller networks into a larger network. And that way, like, larger Bluetooth networks can be formed. So the master coordinates communication throughout the piconet. It can send data to any of its slaves and also request data from them as well. However, slaves are only allowed to transmit and receive from their master, unless with the caveat that it's a bridge slave. Just a brief mention on addresses and names. So this is very similar to like if you had a NIC in like a modem or something of that nature, but each Bluetooth device has its own 48-bit address called bit adder, and it's presented in a 12 hex value. The first 12 bits are the OUI, which is again the same as like the MAC address on a NIC, and then the second 24 bits are unique. And then devices can also be renamed to something more user-friendly for ease of use. Okay, so this is a brief overview of the connection process, and this is connection process for Bluetooth Classic, but it's very similar to Bluetooth LE and beyond. So you have inquiring, or in Bluetooth LE would be advertising, and then paging, which is the actual process of connecting. And then once you have a connection, you have different modes that the periphery or the slave nodes can be put in, and we're going to go through those. So inquiry or advertising, it's stated when 2 Bluetooth devices know absolutely nothing about each other. So they're basically trying to find each other. One's got to run an inquiry or advertise to try to discover the others. And on the flip side of that, so the other device would be scanning, and these could be done simultaneously. So one device could be scanning and advertising at the same time, because Bluetooth devices can act as server and client, kind of in that way. And in this case, they're sending out the inquiry request, but I mean, inquiry and advertising in my research have kind of been synonymous. So you can think about them in the same way. So paging is synonymous with connecting, and paging is a process of actually forming that connection between two Bluetooth devices. And then before this connection can be initiated, each device needs to know the address. So we talked about the addressing earlier. It needs to know the address of the other, which is given out in the inquiry process. So basically, one device will be like, "Hey, I'm advertising or I'm inquiring." They'll be sending out packets, and then another device will be scanning for those packets, and they'll say, "Okay, I found it," and then it'll send back a response basically with its address. Or all of the devices that are found will send back a response with their address. So communication can begin if necessary. Okay, so once we are connected, the device can be put in any of the following modes by the master. So basically, imagine we have a master node and it's connected to one or more slave nodes. Those slave nodes can be put in different modes. So one of those is active mode, which is basically just regularly connected, as far as I can tell, where the device is just actively transmitting or receiving data. So it's just active, it's consistently transmitting and receiving. Sniff mode is a power saving mode, which I imagine would probably be used a lot more in IoT devices and BLE type of devices. Where the device is less active, it kind of sleeps and only listens to transmissions at some time interval, which is set by it can be configured, set by the user, or set by whoever is manufacturing the device. Hold mode is temporary power saving mode, where a device sleeps for a defined period and then returns back to active mode when that interval is passed. So basically, the master's like, "Hey, we don't need you right now. Sleep for this amount of time, and then kind of get back to me." And then park mode is basically like, "Hey, we're not going to need you for a long time. I will let you know when I need you to wake back up and do something." So, and with BLE, I believe you can actually have seven devices that can be connected, but there can be up to 255 devices on park mode, but only 7 active at one time. So I thought that was interesting as well. Okay, so there's also this idea of profiles, because so far we've defined how the devices communicate over the air, kind of what their connection establishment procedure is, and now on top of all of that, there's this idea of profiles, which set specifications or rules that determine how that particular device is used. So what I mean by that is, what if you had a hands-free, Bluetooth, or a heart rate monitor, or any one of these other Bluetooth devices we use all the time? Well, these profiles set specific rules and things and ways that they are allowed to communicate, to kind of make things easier and make their job more specific. So some of the common ones are A2DP, which is Advanced Audio Distribution Profile, and this allows streaming audio from a source to a sync. For example, when you stream music from your iPhone to your car, or from your iPhone to headphones, or something like that, this is the A2DP profile. There's the HFP, the hands-free profile, which uses a Bluetooth headset. So, back when people used to have their little Bluetooth headsets, like my dad had back in the day, that's what would have been used there. I'm not really sure if this is used a whole lot now. Or maybe it is. I'm not sure, but that may have been kind of one of the things of the past. But there's also SPP, serial port profile, which emulates serial ports over Bluetooth, and this is used a lot with Classic. And when we actually look at the stack, you'll see that Bluetooth Classic and BLE have two completely different stacks, and this SPP is basically emulating those cables, those R232 cables for data transfer, and this is kind of the profile that goes along with that. PBAP is phone book access profile, so this allows you to access your contacts or stored contacts. MAP message access profile allows access to phone book. And let's see, AVRCP is remote control, which basically would be like when you have a remote control device for your TV or a fan, or one of those, this would be the profile that would be associated with that. Okay, so now on to the stacks. Okay, so let's start at the physical layer. So basically everything from here down is the same between Bluetooth Classic, Bluetooth Dual Mode, which is the Bluetooth Smart. I forget the other word now, but basically it's a combination of Classic and BLE for like devices like tablets and laptops. It's the combination. And as you can see, it has support for both stacks. But basically everything's the same on all of them up to here. So we'll start with the physical layer. So the physical layer is concerned with the actual transmission of data via radio waves, which we kind of touched on earlier. The Bluetooth radio interface also uses a modulation technique called Gaussian frequency shift keying, or GFSK. This form of modulation is structurally efficient and also enables the use of radio power amplifiers, and thereby saving on battery life. So this is kind of like the base level shift keying. There's also two other kinds. There's pi over 4 DQPSK and 8DPSK, which allows data rates up to 2 megabits per second and 3 megabits per second to be achieved respectively. And if you remember when we looked at the direct comparison between Bluetooth Classic and BLE, DQPSK and 8DPSK, those are both used for Classic because they allow faster transfer rates, and it's not easily supported here. I believe it's a hardware constraint, but it's not really necessary either. This simpler GFSK is sufficient. So those other modulation techniques are typically only used with classic Bluetooth. Okay, next we have the link layer or link manager, depending on which stack you're in, but they more or less do the same thing. They're a combination of hardware and software that are responsible for advertising, scanning, or I guess in our case, inquiring or advertising, scanning, and also establishing the logical links between the connections between Bluetooth devices. So other main functions are device authentication, message encryption, and negotiation of packet sizes. So this is actually where the Bluetooth structure really is implemented, and it's the layer that defines two distinct interaction patterns between devices. So one of those is connectionless communication, in which two devices act as advertiser and scanner, where the advertiser broadcasts data packets and the scanner receives them, which you've touched on a little bit already, and then connection-based, where the scanner and advertiser are able to establish a bidirectional connection and adopt the role of master and slave. So we've touched on both of those. And this is the layer in which that kind of paradigm is established. Okay, the next is the human controller interface, which allows interoperability between the host and the controller. In other words, it's a standard protocol that allows information to be communicated between the host and the controller. And the link layer and the physical layer are collectively referred to as the controller, and then everything above the HCI is referred to as the host collectively. And if you notice, the host is where things actually start getting different between BLE and Classic. Before we get into the differences, we'll talk about this last layer that's the same. So this is the L2 CAP layer, or the logical link, control, and adapt protocol. This provides data encapsulation services and also data integrity to the upper layer. So similar to the transport layer in the IP stack. It ensures retransmission of lost packets, but only those packets that are sent after a connection or after a connection is established are retransmitted. You think you're willing to care about those. If we're inquiring or advertising, those packets are more or less meaningless as they're going to be broadcast continually. So we really only care to, kind of enforce integrity for the packets that we send after connection. Okay, so now let's look at classic Bluetooth, and these two, the RF-COM and the serial port profile SPP. Those are kind of all. I mean, they're two separate layers, but they're wrapped into the same thing. All this is really trying to do is emulate that communication between the RS-232 wiring, or the physical wire that would have been in place. This is just trying to emulate that. So the RF-COM is a simple transport protocol which provides emulation of the RS-232 serial ports over the L2 CAP protocol, so that's what we just said. And then the serial port profile is actually the one that defines the specific protocols and procedures that are used by the Bluetooth device for that cabling. Said another way, it allows each connected device to send and receive data just as if they were physically connected. So nothing too complicated there. I'm sure you could read more into it if you're interested, but this really isn't that heavily used anymore. It seems like this is the more heavily used of the two. So, okay, the ATT is the attributes protocol, and that stores services, characteristics, and related data attributes in a lookup table. So that's kind of a short definition, and I'll go back into it after I tell you what the GAT is. So the GAT is a generic attribute profile. So this defines the way that two BLE devices transfer data back and forth. It's using concepts called services and characteristics. So you can think about it, the GAT goes to the AT and looks up a particular profile, and that profile contains services and characteristics. Okay, Services are used to break data up into logical entities and contain specific chunks of data called characteristics. Services can have one or more characteristics, and each service distinguishes itself from other services by means of a unique numeric ID called a UUID, which can either be 16-bit for official BLE services, and it can be custom 128-bit for whatever you decide. And then the lowest level concept is that idea of the characteristic, which encapsulates a single data point. Though it may contain an array, but basically it could be something like an XYZ value from like a 3-axis accelerometer, or it could be like a temperature value, or it could be a heart rate value, or something from one of your Bluetooth devices could be encapsulated in this lowest level, or some single data point, or some single type of data point, I should say. Okay, and then there's one that's not listed here, but I think it's worth talking about. There's this idea of the generic access protocol that's actually sits kind of next to or above the GATT here. And it's the layer of the BLE stack that's responsible for connection functionality. This handles access modes and procedures of the device, including device discovery, link establishment, termination, initiation of security features, and device configuration. More simply, it really just controls connections and advertising in Bluetooth. It's really what makes the device visible to the outside world and kind of determines whether two devices can or can't interact with each other. For example, like if this BLE device was trying to connect to a Bluetooth Classic device, GAP would be the one that would be like, hey, we're not compatible. So that's a pretty brief overview of the Bluetooth stack. Oh, and just as a note, this middle profile is the combination of Classic Bluetooth and BLE. Okay, finally, we're just going to take a brief look at packet structure. And the packet structure has a preamble, an access address, a PDU, which is a protocol data unit, which is basically, think of it as a payload. I know it says payload here, but really it's just a payload with a header, more or less. And then the CRC is used for error detection. So basically, the preamble is used for synchronization. It's a 1-byte predefined pattern. So for example, an advertising packet is 101010 in that order for 1 byte to kind of let you know that it is a advertising packet. And then there are other preambles based on different types of packets. So the access address for all advertising packets is fixed in a certain pattern. For all data packets, it consists of a 32-bit random value generated by BLE devices in its initiating state, and the same value is used in a connection request. And as we said before, the PDU is kind of the payload, but we have two different kinds, or two main types of PDUs. We have an advertising type of packet, and we have a data channel type of packet. And each of them contain a header, and one is just significantly larger than the other. And then we also, with the data channel, after we've established a connection, we start using this data channel, right? So we have these MIC, or message integrity checks. And this is used if there's any kind of encryption that we are using with Bluetooth. And there you have it. So there's Bluetooth packet structure. And then I just want to give a quick list of references I used to compile this. So here's my reference links. I'm just going to pause here for a second so that if you want to take a look at any of them, you can. All right, guys, thanks for watching. I really do appreciate it. Again, guys, if you enjoyed the content, please consider giving me a like and subscribe so I continue to grow and produce better content. Also, please feel free to give me some feedback in the comments. Let me know how I'm doing, or if anything's unclear, or maybe there are other ways I can improve. But thanks again, guys. I really appreciate the watching, and have a great rest of the day.